Everyone, I'm Davide Scaramuzza, and I'm professor of robotics at the University of Zurich, and I'm also affiliated with the Institute of Neuroinformatics of ETH and the University of Zurich. I've been working on autonomous drones now for 13 years, in fact, and in robotics for 18 years. And I want to tell you basically the journey that took me to where we are now. In particular, I want to tell you about autonomous, agile, visual controlled drones. But let me start by basically having an overview about today's global commercial drone market. So we read a lot in the news about drones. In fact, drones are actually the most used mobile robot out there. There are more than 100 million drones worldwide. And at the moment, the global commercial drone market is worth $24 billion. But what is interesting now is that if you look at the most profitable market sectors, these are inspection, media entertainment, agriculture, and law enforcement. For example, what you can see in this report that was published just a few months ago by Groundview Research, the inspection market represents almost 50% of the whole global commercial drone market. Basically means that the most commercial drones are being used for inspection of bridges, power lines, difficult infrastructure like combustion chambers of nuclear plants or thermal plants, and also railways and more. Then the second largest sector is media and entertainment. So it means that actually there are 20% of all commercial drones that are being used for making films, for also photography, videography, and also for movies, including Hollywood movies, for example. Then 15% of the market is for agricultural drones. So these are drones that are being used for spraying pesticides. And then there is another 15% of drones that are being used by law enforcement, for example, for monitoring people, crowd gatherings, and so on. And interestingly, the drone delivery market is only 5% of the whole commercial drone market. And this is very interesting for me because if you look back at the market predictions, the experts were predicting that the largest drone market would actually be delivery by 2020, and this didn't turn out to be true. Another interesting thing, if you read this report, is that, however, in the future, it could be possible that the drone delivery will actually grow. And the global commercial drone market is also expected to grow to 500 billion by 2028. So these are actually very good news for the drone research community. Now, what is also very interesting for people who do research on drones is actually that when you look at the autonomy capabilities of all commercial drones, well, they're not very autonomous because they are, most of them, controlled by human pilots. And only a tiny percentage of them is controlled by GPS. Now, how do humans control drones? Well, they control drones, for example, either with the direct line of sight, or, for example, by putting a camera on board the drone that relays the signal to some goggles. However, to fly drones with a remote controller, it takes several months or even years of experience. Then the second way is to rely on a GPS-based autopilots. And so all the commercial drones that fly above our heads, beyond line of sight, are actually controlled remotely via GPS. That means that basically they rely on the constellation of hundreds of satellites around the planet. But the problem is that GPS does not work indoors. And second of all, even outdoors is not very reliable because, for example, when you fly very close to structures under the tree canopies, or for example, in urban canyons, then the signal is obstructed, which causes the GPS to actually estimate the position wrongly. And this can actually lead drones to crash. For example, what you see in this Swiss news from 2019, a drone carrying blood fell in the Lake Zurich due to GPS failure. And unfortunately, as the number of autonomous drones is increasing over the years, so will increase also the chances that they will actually fall. And actually, the interesting fact is that there was also a second crash after the first crash in Zurich, and the second crash occurred next to a kindergarten. where kids were playing. So the issue is actually very, very concerning. In fact, what you need to consider is that all GPS-based drones fly completely blindly, so they don't see anything. So the question that I've tried to answer over the past 13 years of research is how can drones navigate autonomously without GPS? The answer is by using cameras. What you can see in this video is, for example, an autonomous drone that is using a single onboard camera to stabilize itself. This was a demonstration we gave 13 years ago, in 2009. Here the drone is being disturbed and basically is able to use a single onboard camera for stabilization. How does it work? Well, what you can see in the top right video, that one is actually the onboard video, and you can see that we are detecting grip points. These points are basically called features. These are points with the high contrast that is easy to redetect when the drone navigates, and we use them as reference points. So if the drone is disturbed, it tries to restabilize by keeping those points exactly where they were detected in the first place. And the interesting thing is that you can use the same technique now also to map the environment. And once you have a map of the environment, you can then navigate autonomously because you can identify obstacles, and then you can also set the waypoints and also the destination that you want to reach. And this was the first vision-based autonomous flight, September 9, 2009. It was at the European Micro Aerial Vehicle Competition, which we won in the autonomy track. It was the first vision-based autonomous drone. At the time, the regulations didn't allow to fly drones freely, so we had to secure the drone with a fishing rod, which you see here. The drone was autonomous, but was just secured in case things wouldn't turn out nice. Also, the other interesting fact was that at that time, the computing power to do the whole mapping and the motion estimation was not capable of running on board, but only off board. And so we streamed the images to an off-board laptop using a 20-meter long USB cable. And here comes the moment when the drone is supposed to enter a small window. And first we pass the fishing rod, and then we pass, the drone passes. And on the right, you can see basically what the drone sees. On the top right, you can see the camera on board the drone with the detected features. In the bottom right video, you could see basically the map being expanded in real time. So this was in 2009, 13 years ago. Where is now this technology? Well, the guy that you see in this picture is Stefan Weiss, who then flew to JPL, NASA Jet Propulsion Laboratory, and now this technology is on Mars. So the Mars helicopter Ingenuity, made by NASA, actually uses a similar navigation algorithm that we were using 13 years ago. So it's using a single onboard camera and an onboard computer. And what you can see in the bottom right is exactly the features that is extracting. So it's building a map in real time that then it uses to stabilize and follow a given trajectory. So it's been 13 years, but now we can say with confidence that vision-based autonomous navigation is available for the market. And there are several companies that are now using it. For example, a very successful company is a Californian-based company called Scaramuzza that is using drones for inspection of bridges and difficult infrastructure. And what you can see in this video is that the drones navigate only using onboard cameras. So they can be flown either completely autonomously or with the intervention of a human, but now the human doesn't have to basically send control commands at very high detail, but rather very high-level commands. For example, move at a constant speed, avoiding all the obstacles, and take pictures every 1 meter. So you can actually now do this thanks to onboard vision-based autonomous navigation. And so now that we have drones that can fly basically autonomously with onboard vision, the question is what's next? So as I told you, this was something that I was working on for 13 years ago. But actually, in the past few years, we have tried to make now drones much more agile. Why? Because if you look at the performance of autonomous drones compared to the human pilot performance, well, there is a huge gap. And to see what I mean, look at this video. What you can see in this video is not an autonomous drone, but a drone piloted by a human pilot. So there is a camera on board the drone that transmits images with 10-20 milliseconds latency. Then the human brain processes these images. The human brain is quite slow. It takes 220 milliseconds, and then computes control commands that are sent via the remote controller. What is very interesting about human pilots is that they're able to navigate at impressive speeds using just onboard cameras, so basically vision-based, and all this with an incredible robustness, despite the motion blur and the high dynamic range changes that occur at these speeds, and also despite the latencies involved. So the question that I've been trying to answer over the past few years in my lab is what does it take to fly as good or even better than human pilots? We call this problem agile flight. And you may ask, why do we care about flying agile? Well, the first reason is actually purely practical. By making drones faster, they will be able to actually fly longer distances. So making drones faster increases their range. And you can see what I mean exactly in this plot, where you can see the distance flown by the drone in kilometers and the flight speeds in meters per second, so from 0 to 10 meters per second. The drone that we are reporting here is a DJI Phantom drone. So you can see that actually in many inspection tasks, the drone is actually controlled at very low speeds of half a meter per second. So that means actually they can fly only for less than half of a kilometer. But as you fly the drone faster and faster, you can actually cover longer distances. By the way, these distances are calculated exactly as explained in this paper that we just published, considering the maximum battery life of the drone. Now, the problem is that the battery life of a drone dies after 20 minutes or 30 minutes, depending on the type of drone that you're using. And so if you fly at very slow speeds, actually you can cover very small distances. But if you fly at faster speeds, you increase actually their range. And so the utility of the drone. You can fly, you can see that if you fly at 6 meters per second, you can reach distances of almost 3.5 kilometers. However, if you fly faster than 6 meters per second, what happens now? The maximum distances that you can actually reach before the battery dies now reduces again. Why? Because at faster speeds, then you have a more drag, so the resistance from the air, and also you are consuming more energy. But so the bottom line of this plot is to show you that basically it makes sense to fly drones faster to improve their utility. Another reason why we care about making drones agile is for all those missions that are time critical. For example, search and rescue, delivery of packages, inspection and exploration, flying cars, and also space exploration. Another reason is actually purely intellectual. Actually, flying agile raises very difficult challenges for robotic research, especially for perception, planning, learning, and control. And so for me specifically, and all the people that work on computer vision, it allows us to push the limits on vision-based navigation. And that's why I love this research topic. What you can see in this slide is the autonomous drone that we have been using over the past years. Its name is Barracuda. So it's a friendly name and means fast. And it has basically an onboard computer that is basically the brain. It's an NVIDIA Jetson TX2 that we use for neural network inference and flight control. Then we have an inter-real sense for example, state estimation, and an inter-real sense D435 for depth maps, so for obstacle avoidance. This drone can actually accelerate from 0 to 100 kilometers per hour in less than 1 second, can reach speeds that go over 130 kilometers per hour. It has a weight that is less than 1 kilo, maximum thrust 70 newtons, and thrust to weight ratio of 5. So it's quite agile, it's very capable. Now, how do you control a drone? Well, you control a drone very much like you control any other mobile robot. So basically, the input are sensor inputs, which means, for example, images and inertial measurement units. These are inertial sensors. Then there are three modules: perception, planning, and control. Perception typically does state estimation, so it computes the position, velocity, and attitude of the drone. It also computes local maps to identify obstacles around the environment that you want to avoid. And then this information is sent to the planning module that computes a collision-free trajectory that is then executed by the control module that then computes the low-level control commands, for example, like the rotor speeds. Now, there are several issues with this architecture, because despite it has been used for 40 years in robotics for mobile robots, it actually has some shortcomings for agile flight, so for agile autonomous flight. The first has to do with the fact that when you navigate very fast, you're going to have very imperfect perception. This is because of at high speeds, you will have a lot of motion blur, light changes, and also the limited field of view will cause a lot of features that you need for estimation to actually fall outside of the field of view. To see what I mean, look at these pictures. This is, for example, a typical motion blur scenario that you have when you're flying fast. Also, when you fly fast, there are sudden changes in illumination that again causes state estimation to fail. And finally, also another problem are aerodynamic effects, especially at high speeds, that are very difficult to model, because actually these are basically this is turbulent flow that you cannot model easily mathematically, unless you require sophisticated fluid dynamic simulators. So we are talking about computational fluid dynamics. Another problem with the vision-based drones is that in order to fly, they need to constantly observe features in the environment. Just to give you an idea, if you have a drone that has a downward facing camera, so if a camera facing down, for the drone to remain stable in the air, it needs to constantly observe features on the ground. That means if there are no features, the drone will actually drift and crash. And that happens often with vision-based drones. Now, the problem becomes even more difficult, because if you want to now reach a given point, at least somewhere else, the drone needs to actually, direct its heading towards the point you want to reach. And by doing so, basically, you may lose the visibility of point of interest. So to avoid this from happening, you need to create a synergy between action and perception. So you basically can only fly trajectories that facilitate feature tracking. We call this problem perception-aware planning and control. Another problem with this traditional control architecture is the high latency due to the sequential structure of this architecture. So the fact that we have concatenation of perception, planning, and control, each one with its own latency. So in the end, you actually have a compound latency that limits the maximum agility of the drone. You can understand that in order to be fast, you need to be able to process the images and generate control commands before the next image arrives. So you need to actually be faster than the frame rate of the camera. And that means actually that any milliseconds that you can save, it's additional speed that you can actually gain. What would be the other alternative way to control a drone? Well, the alternative way to control a drone would be to use a neural network. A neural network, exactly like humans and animals like birds actually use. Neural networks, like our brain, can actually map directly images and inertial readings to control commands. Think of yourself as a person. So we know this works, but the problem is that at the kind of state of the art, this is very difficult to do, because for training a neural network end-to-end for specific tasks, actually you need tons of data, which is very difficult to get, especially in the real world, like on a physical drone. Another problem is the limited interpretability of using just a neural network. So what we have been working on over the past few years is trying to augment the traditional robot navigation architecture with the learning-based methods. But now when you use learning-based approaches, the key question is, should we train it with or without supervision? And how do we get enough training data? Can we learn in simulation? And if we train in simulation, how do we address the simulation to reality gap? So, you know, simulation and the real world are significantly different. How do you make sure that if you have trained the network in simulation, will transfer to the real world? So we have been trying to answer these questions in the framework of 3 different tasks. The first task is autonomous drone acrobatics. The second task is navigation in the wild, and the third task is autonomous drone racing. So let me start with the first approach. I hope you can see the video. So in this work, we were able to train a neural network that takes as input images and maps them directly to control commands to achieve agile acrobatic maneuvers that are similar in speed and accelerations to those performed by expert human pilots. Actually, for these maneuvers, the drone reaches acceleration of up to 3 Gs, which is exactly what human pilots experience. All this was done using an onboard camera and an onboard computer. And if you're interested, by the way, the code is fully available since more than a year. So all the data sets have been made available, and also this code is completely available. How did we train it? We train it only in simulation. That means we did a one-shot sim to real transfer. It means that we transfer then the trained policy to the real world without any fine tuning. What you can see is the simulation that we actually did. We used the gazebo in this case. We simulated hundreds of drones, tracking hundreds of different aggressive maneuvers. And we simulated basically 50 flight hours for each drones in just 5 hours. So within a night, we were able to train the algorithm. And then once the algorithm was trained, we downloaded the network and we deployed it to the real drone. And we show in the paper that not only did it transfer to real drones, but also different real drones. And here you can see in this video that the same policy trained in simulation was transferring exactly identically to the real world. But now the key question when you train in simulation is how do you make sure that it transfers to the real world? There is no guarantee that it will work in the real world. Well, first of all, we have to say we have very good physics and modeling of the drone. But in order to actually generalize this, we do a little bit of domain randomization. So we randomize a little bit the mass of the vehicle, the center of mass. Also in this case, we randomize a little bit the radius of the loops, for example, in these loop trajectories and so on. But actually, how did we actually train a neural network in the first place? So we trained this neural network using privileged imitation learning. What does it mean? It means that we use a neural network which tries to imitate the control commands output by an artificial expert. So basically, the neural network is being trained exactly as you would train a kid to mimic its parents. Basically, the neural network predicts commands that you want to match with the control commands output by the artificial expert. So first of all, what is the expert? The expert is not a human pilot. You do not want to mimic a human pilot because you want to be better than human pilots. So in our case, we use an artificial expert. What is an artificial expert? It means an algorithm that can know how to solve the task. For example, in this case, we used model predictive control, NPC, nonlinear model predictive control. However, this expert is privileged. What does it mean that an expert is privileged? Well, it has a perfect knowledge of the robot state and of the environment. And now the question is, how can an algorithm that we use for training now have a perfect knowledge of the robot state and environment? Well, it can if you do training in simulation. So we do the training in simulation because in the simulation, we know perfectly the position, velocity, attitude of the drone. We know exactly where we want to be. And we know perfectly the environment, okay? So we try to imitate the control commands output by this expert. So saying this in different terms, we distill the knowledge of the artificial expert into a neural network. If you're interested in the details, the neural network we used here was a temporal convolutional neural network. Now, the question, though, is how do we make sure that the network trained in simulation transfers to the real world without fine-tuning? As you can see, the problem is that the simulation and the real world are completely different. In this work, 3 years ago, we actually used Gazebo, which is, as you know, a non-photorealistic simulator. And here we simulated, for example, some ground plane where we added some pictures from the internet and also some Windows images from the background. And you can see here, instead, the real world looks completely different. So how did we make sure that a vision-based drone can work in the real world, trained only in simulation? Well, the trick is to use an intermediate sensory abstraction. So that means we are not training on raw image pixels. We are not training on this. We are training on feature tracks. So actually at simulation time, we generate the feature tracks as the robot navigates. And then we expect that these feature tracks will be similar in the real world. Were they similar? Actually, they were similar, because what we prove in the paper is that actually by using feature tracks as a sensory abstraction, we reduce the Wasserstein distance between the observation models in simulation and the real world. So it actually works. We proved it. And not only we proved it, but it also showed to work in the real world. Now let me move on to another task. The task of navigation in the wild. So what does it mean in the wild? Navigating in the wild, it means navigating in unknown, unstructured environments. This can be, for example, forests or, for example, unknown environments in general. Let me start with a video as usual. What you see here is our drone that is navigating in a forest, in this case, and it's flying very fast. In this case, it was actually pillars outdoors. Here it's exiting a hangar. This one is a commercial drone called the Skydio. This one is again our autonomous drone. We could fly at speeds up to 10 meters per second, which is almost 40 kilometers per hour. And we could also fly, for example, with a little bit of fog, again, with a vision-based drone. If you're interested, by the way, this drone, again, is fully vision-based. It uses a single onboard camera and onboard computer. The same computer and sensor I showed you before. It's the same drone, using a Jetson TX2. And if you're interested, again, all the data sets and the code are available open source. They're available on GitHub. Just look for the paper. Now, how did we train it? We trained it in simulation. We use a simulator called Flightmare that we open sourced 2 years ago. And simulation, again, why simulation? Because simulation is fast, it's cheap, and especially it's safe. So you can actually generate almost unlimited amount of data in just a few hours, and it's super safe because you don't hurt any people, neither the environments. So you cannot do this in the real world. You cannot fly and train drones in the real world because it would be significantly dangerous. But you can do this in simulation. So let me show you the simulation environment in this video. So basically, it's a simulated forest. Where did we get this simulated forest from? Well, we downloaded it. We bought it from scenarios that are available for video games like Unity. So there are hundreds of different forests that you can download for just 50 euros. So we downloaded a few forests, and then we simulated our drone. So we imported our drone in this simulator. Actually, what we did is that we imported the simulated scenario into our Flightmare simulator. And then we trained our algorithm. How did we train the algorithm? Again, we used imitation learning. So we actually tried to imitate an artificial expert. What was in this case the artificial expert? In this case, the artificial expert was a model-based algorithm that has privileged knowledge about the environment. So it knows perfectly the state of all the drone, so its position, velocity, and attitude, and it knows the position, diameter, and density of all the other trees. So it knows exactly where all the obstacles are. But this is because in simulation, so this is a privileged algorithm. And then what do we do? In simulation, actually, let me rewind the video. In simulation, we can generate a collision-free global trajectory that can fly the drone safely from the start to the finish. So you could already train in simulation to ask the neural network to imitate the control commands that would take to fly this single global collision-free trajectory. But we don't do that. Why? Because if we want that in the real world, the train policy is capable of also coping with ambiguities. For example, when you have those two slits, where do you go? Do you go left or right? Well, if you train, basically you would actually bump in the middle. So we actually don't don't imitate a global trajectory, but what we imitate is a multimodal distribution, which is what you see here. All these thousands of trajectories are a multimodal distribution that we generate with Monte Carlo sampling. These trajectories are all collision-free within the next 10 meters. So that means that none of these trajectories collides with any obstacles in the next 10 meters. Since we are flying at 10 meters per second, it means basically, that they have to be quite fast. Here you can see that these trajectories are really collision-free again. So we ask the neural network to mimic the distribution of these collision-free trajectories within the next second of flight. But again, the problem is that we want to make sure that the network trained in simulation can transfer to the real world without any fine-tuning. How would we make this possible? Remember what we did before? The trick is to use an appropriate sensory abstraction. And here, as a sensory abstraction, we use depth maps. Why? Because you can see that depth maps are very similar both in simulation and in the real world. They are independent of the texture. They are also independent of the color, no matter what seasons we are in. So it doesn't matter whether the tree canopy is yellow, red, or green, because the depth is always the same. Also, it doesn't matter what the color of the tree trunk is or what the color of the bottom is, because it's only depending on the depth. And you can immediately perceive that the depth in simulation in the real world looks similar. Now, the big question is, when you train on depth images, on depth maps in simulation, the big question is, since now your simulator has a perfect knowledge of the environment, you could, in principle, train on the exact depth map. Does it make sense? On the exact depth map. Well, we show in the paper that if you train on the exact depth map, it wouldn't work as well in the real world as if instead you train on realistic depth maps. What does it mean, realistic depth maps? Well, in the real drone, we have a stereo camera. Depth maps are generated by running left-right stereo matching on the two left-right images. And you can recognize that this depth map is actually obtained by stereo matching because each tree trunk has the typical occlusion artifacts around its edges. Do you see these white edges that I'm indicating? These are actually due to occlusion artifacts, due to the fact that basically the left and the right camera are at different positions, and therefore there is occlusions. So what we show in the paper is that if you train on realistic depth maps, so on noisy depth maps, actually the transfer to the real world is much more accurate than if you train on exact depth maps generated from the ground truth. This is the video of what the simulated drone sees in simulation. So these are the simulated depth maps that we are training upon. Now let's go to the results. So I told you about training in simulation, but we want to understand how well it works now in the real world. How does it compare specifically to use a neural network instead of the traditional model-based baselines? Well, what we showed in our paper, let me first give you the results, and then let me comment on the quantitative results. The first thing that we discovered is that first of all, using a neural network is up to 6 times more efficient than the traditional baseline of state estimation, planning, and control. It is also much more robust and much faster. In fact, at speeds of 10 meters per second, our success rate dropped to only 60%. So we can basically fly twice as fast as the traditional baselines. So let me now comment on the quantitative results. So what you see in this table are 3 different algorithms. The last one is ours, so the neural network controller. The first two instead don't use a neural network, but these are basically using the traditional algorithm. These are also open source algorithms. They're very famous. This is basically the state of the art. And Fast Planner is from Hong Kong, University of Science and Technology, Professor Xiaojia Shen. They have a lot of algorithms for planning in the wild that are also available on DJI drones and have been open sourced. As you can see, you know, pre-processing, mapping, and planning are pretty slow. And the overall processing latency of all the images takes 65 milliseconds. Okay, so it's actually double than the frame rate of the camera. And this is not good because the frame rate of the camera is 30 Hz. So ideally you want to be faster than 30 milliseconds. This one instead is another algorithm from MIT, Professor Rusty Drake's, also available open source. This one is reactive. It's less precise because it takes makes decision reactively. And so being reactive, though, is faster than the other one, it takes 20 milliseconds. While ours instead is much faster than the two model-based baselines, because ours requires only 10 milliseconds or 2.6 milliseconds if you process them on a powerful GPU. So 10.3 milliseconds if you run the algorithm on the Jetson TX2, or 2.6 milliseconds if you run the algorithm on a desktop GPU. So we are twice as fast as reactive and 6 times as fast as a fast planner. Let's comment on the success rate. So this is very important when you work on robotics, mobile robotics. You want to always plot the success rate. And in this case, since we are talking about agile drones, we want to plot the success rate with respect to the speed, so the agility of the platform, from 0 to 10 meters per second. So you can see that ours is actually the one in green. So it's our neural network controller. We reach 100% success rate up to 5 meters per second. And then the success rate shrinks to 60% at 10 meters per second. So we can still fly at 10 meters per second, but that means we could crash 40% of the time. But we could reliably fly 60% of the times. If you now look at instead at the model-based baselines, well, we can see that already at 5 meters per second, the fast planner, basically already the performance drops to 20% at 5 meters per second, while the reactive approach, which is faster, because it's faster, basically can handle well speeds up to 5 meters per second with a success rate of 70%, but then it drops very quickly to below 40% already at over 6 meters per second. So I hope with these results, I convince you that by using neural network controller, we are not only faster, but we are also more robust to noise, because this is also a cause of failure cases. And now let me talk about another very exciting work that we have been doing over the past 5 years, which is autonomous drone racing. So vision-based autonomous drone racing. What you see in this video is an autonomous vision-based drone that is doing a drone racing task. So in drone racing, the drone is supposed to fly as fast as possible. So it wants to minimize the flight time from the start to the finish while passing through a sequence of gates in a given order. You can see this one is vision-based, using an onboard camera and computation, exactly the same drone I showed you before. And here are the onboard gate detection that it uses for state estimation. And now this one is much more recent. Here, I don't have time to go through the details, but actually here we use now reinforcement learning rather than imitation learning. Why? Because we want to beat also model-based algorithms. So what we found out is that any model-based artificial expert is actually suboptimal. So the only way is to actually then trying to learn models in the real world. And for this, we actually deployed a reinforcement learning approach. And now another thing that we're also working on is trying to beat the best human pilot, which I'm happy to anticipate that we did. So we actually invited to Zurich world-class human pilots. In particular, we invited the best human pilots from the US, the best human pilot from Australia, and also the best human pilot from Switzerland. And I'm happy to report that we were able to outrace all 3 of them in speed. Here you can see some close-up scenes from the race. This one is the youngest of the pilots, and actually also interestingly, the most aggressive, Marvin. So Marvin surpassed in terms of speed even the US champion, the Australian champion, on this track. It really depends on the track. And the blue one is the AI drone, and the red one is the human piloted drone. And this is completely vision-based. Now, the big problem, though, when you work on drone racing is aerodynamic effects. So see what I mean here. Here, the drone is flying super fast, 70 kilometers per hour, and is making a very sharp turn. And when you make these turns, you generate a lot of turbulent flow. This turbulent flow, that means you can only simulate it with the computational fluid dynamics, CFD, which would take hours or even days of computation. So, and it would actually be trajectory dependent. That means every time you change a little bit of trajectory, you would have to generate new simulations, which is just impractical from, from an engineering point of view. If you want to deploy this race, you want to be able to train, within 10 minutes, not days. So, because humans are able to adapt within minutes or hours, not days. So how do we handle aerodynamic effects? So you can model linear aerodynamic effects like linear rotor drag, fuselage drag very well. You can also model higher order aerodynamic effects like the blade folding using a blade element momentum theory. You can use this to basically predict within a certain degree the forces and torques acting on each propeller. But actually that only explains 40% of all the residual forces and torques. So to explain the remaining residuals, actually we are now leveraging neural networks. This is work that we published at RSS in 2021. Basically the idea is that we use a neural network, in particular a temporal convolution neural network, to model the residual forces and torques that cannot be explained by the first principle blade element momentum theory. So we train a neural network. How do we train a neural network? In this case, we train it with supervision. So we have a flight room where we can record the trajectories executed by the drones. And so we can actually compare the executed trajectory with the trajectory estimated by the dynamical model of the drone, so using the blade element momentum theory model. And then what we are trying to do is that we use the neural network to model these residual forces and torques. So we try to model basically the residual gap. And actually, by doing this, we can improve the realism of our simulator by up to 60%. Up to 60%. So basically what we're doing is that we are realifying our simulator, and then we can fine-tune in simulation, deploy again in the real world. If you're interested, by the way, the code and the datasets were released. You will find 20,000 trajectories of autonomous drones flying at over 70 kilometers per hour, from 0 to 70 kilometers per hour, so random trajectories. And now what's next? What's next for research? So, well, what is faster and more agile than humans in the future? So this is actually more farther in the future. So once we are capable of, of outperforming human pilots in different tasks, the next work will try to make autonomous drones fly even better than birds. And look at what sparrowhawks are capable of doing. Here you see a sparrowhawk that is able to fly around an obstacle, slalom among trees, pass through a narrow gap, and finally make the little bird magically disappear. How come that birds, animals, are actually so fast? Well, to go faster, we need faster sensors and algorithms. At the current state, the agility of a robot is limited by the latency of its sensing pipeline and perception action pipeline. So to explain what I mean, just look at this plot. So every time we grab a frame, we have a processing latency, which is basically the time that it takes to the onboard computer to process this frame. Then you need to wait the discretization time of the camera to receive the next frame. So if you have a 30 Hertz camera, like the Intel Sense, that means you need to wait 33 milliseconds before the next couple of stereo frames arrives. And so we refer to this as the sensing latency, okay? Now, the sensing latency, though, can change dramatically depending on the illumination environment. Just think that if you are flying in a bright day, for example, the exposure time is 1 millisecond. But if you fly, for example, indoors, then the exposure time is over 30 milliseconds. And if you fly with artificial light, then the exposure time goes up to 100 milliseconds, so 1/10 of a second. So the sensing latency can change dramatically depending on the illumination conditions. And this is the problem, not only the sensing latency, but also the processing latency. So on one side, you want very fast algorithms, but on the other side, you also would like to have very fast sensors that can actually have a sensing latency that is in the order maybe of milliseconds without being affected by the external illumination. Wouldn't that be a dream? Well, fortunately, such a sensor exists. So can we answer the question, can we create a low latency, low discretization perception pipeline? So can we create a pipeline that has a small processing latency, a small sensing latency? The answer is yes, if we use not standard cameras, but rather event cameras. You can see why. Because event cameras do not output information, a given frame times, but rather continuously in time, asynchronously. What is an event camera? An event camera is a camera that measures only motion in the scene. And look at this video to see what I mean. Here I'm moving my arm up and down, and you can see that only the pixels that detect motion trigger information. In particular, this camera has tiny microprocessors beneath each pixel that constantly monitor the scene observed by each individual pixel. In particular, every time that a single pixel detects a change of intensity caused by motion or caused by a blinking pattern, then that pixel will trigger an event. And these events are colored typically in blue or red, meaning a positive change of illumination or negative change of illumination. And the spurious pixels that you see in background are actually due to sensor noise. Now, the key advantages of an event camera are two: very low latency with resolutions of microseconds, and also no motion blur. But the key thing is actually that these events are actually output asynchronously rather than at constant time intervals. To understand what I mean, assume that the visual stimulus of the event camera is a rotating disk. So there is a disk rotating. What will be the output? The output of the event camera would be a spiral of events in space and time. I hope this makes sense. A spiral of events in space and time, because only the events that detected the motion of the dot trigger the events. And now, if there is no movement in the scene, there are no events. But the cool thing is that if the camera is spun fast, actually there is no motion blur. So the event camera doesn't suffer from motion blur. And so, one more time, the key difference between an event camera and a standard camera is that the standard camera outputs frames at constant time intervals, and that means all the pixels trigger information at the same time, while with an event camera, each pixel is independent of any other pixel and trigger information asynchronously. So let me show you two applications of this. So the first application I want to show you is to keep drones flying when a rotor fails. So what happens when the rotor on an event camera fails? When the rotor on an event camera fails, so when the motor of what happens when the motor of a drone fails? So when the motor of a drone fails, what happens is that the drone starts spinning on itself like a ballerina. This is due to the principle of conservation of the angular momentum. And during this spinning, the drone drifts and eventually crashes. Because with the standard camera, the images are motion blurred. So previously, people were relying on GPS to stabilize this drone, or on external position sensors like motion capture systems. But finally, you can do this with the event camera. And what you can see here, what it does. So here below, you can see the onboard camera images, event camera images, that basically are not affected by motion blur, no matter how fast the drone spins. You can always detect and reliably track features. So not only can you hover, but you can also follow a given trajectory while the drone is actually spinning on itself. And by the way, if you're interested, we release the code open source. So always, most of the code and the papers we write, we release the code. This is another application of event cameras to drones. For example, here we do the task of dodging balls thrown at the drone. Again, using an event camera. And we show that with an event camera, we can do this at latencies of 3.5 milliseconds. With a standard camera, instead, depending on the illumination, the latency will range between 30 milliseconds and 100 milliseconds, making basically the flight speed much lower. So with the event camera, we are not affected by the external light, and we can actually fly at relative speeds of 10 meters per second because the perception latency is only 3.5 milliseconds. This is the overall latency. The sensing latency plus the processing latency, by the way, 3.5 milliseconds. Also, the code is available online and also the datasets. And so this takes me to the final slide. So basically, I've been introducing the topic of autonomous vision-based agile flight as a new research topic. I think to fly reliably drones as human pilots, it will take probably 10 years to solve because human pilots are extremely capable. So the human brain is very slow. It takes 220 milliseconds for experienced pilots to make decisions, but they are still much more robust than machines in complex situations. That's where actually human pilots are extremely good at complex situations. Also, I remember that the reason why we want to work on vision-based agile flight is to push the limits of existing algorithms in extreme situations. And because also it raises fundamental problems for robotics research in terms of planning, perception, learning, and control. Also, what I showed is that you can use learning-based methods to complement the traditional robotics architecture. In particular, because the learning-based methods I showed you are more robust to imperfect perception and exhibit lower latency than traditional algorithms. Then I told you about the problem of training these algorithms, and we spoke a lot about simulation, training and simulation, and then how to solve the simulation to reality gap. And I show you that one trick to make this possible is to actually use appropriate input abstractions of the sensors. In particular, for example, for the task of drone acrobatics, to use official tracks, while for the task of navigation in forest or in unknown environments, to use dead maps. Also, what I haven't talked about is you may want to also use appropriate output abstractions in order to reduce the simulation to reality gap. So if, for example, we have a paper where we showed that if you use, if you ask the network to predict collective thrust and body rates, is much more robust and with higher success rate than asking the network to predict directly velocity commands or, for example, low-level control commands. Also, what I talked about are event cameras that have a much lower latency and no motion blur. And I haven't shown you, but actually, if you couple also event cameras with neuromorphic chips, you would actually be able to allow low latency, high bandwidth control. So you can go even faster. And with this, I would like to thank you for your attention. And this is the team of my lab. And these are all the sponsors of our lab over the past 10 years. Remember that we open source most of the code of our papers. You can also follow me on social media. And if you're interested to do internships or to do a PhD or a postdoc in my lab, I have open positions. Thank you for your attention.